Discover Next, the studio for facades and design. Next is the platform for innovation in the field of building envelopes, for inspiration, information, and communication. Initiated by Vicona, with leading industry experts as Next partners. Next is a unique concept which is constantly evolving and bringing the future of cities to life.
Und Action. Good afternoon, maybe good morning, maybe good evening. Welcome to the Next Studio. My name is Christian Mettlach. I have the pleasure and honor to introduce Uli, our moderator today, and to welcome you to our 7th International Next Facade session. Actually, it's our 4th session. Today we have more than 500 participants.
He says Uli. I'm just Uli. I'm not
Uli.
Uli Knack, I'm just Uli.
Yeah.
That's what he said. There's some of us in this branch which are only having one name.
And that's Uli.
That's
Yeah.
Uli, okay.
So we have more than 500 people registered. We have more than 20 countries, so I think that's a record number of participants.
You're ticking
And
all
the
my
basic-
boxes.
And the basic question is now, are they here because they want to hear about the mistakes, or they want to just see you? We'll find out. It's your stage now, Uli.
Yeah, you're ticking all my boxes. Huh? So
Yeah,
you
I know,
named
yeah.
it International Next Facade Session.
Yeah.
It's named The Truth Is.
Yes.
And yeah, I'm Uli Knack. And I started discussing this with you. And as we were doing this podcast earlier today, we also discussed, is there kind of logic to talk about mistakes you do? No, it's not. And
Lessons learned.
I was in, committees, and I was asked, can we somehow get the grey fox, as one of our Finnish
We
colleagues,
said white rabbits.
white rabbits, teach the youngest? Oh, come on. And then they all show the glorious building they do, all the nice super buildings and all the successes. So I thought, well, let's do the mistakes. Let's do the real mistakes. And that group is now trapped to do this. And I started talking to people, would you be able to show? I can't make it. I have another appointment today. No, I'm traveling. It was really interesting. So you call your colleagues and you call your friends, close friends. They cannot deny. They cannot say I don't come. So they have to come. And it's really interesting. I'm very used to them when they talk. I know most of their speeches. And they called a lot. What am I going to talk about? This is a new one. I have to do a new one. This is not the one which I can take, blah, blah, blah. So that was really interesting. I'm the lucky one not presenting 5 mistakes, but I have 5 mistakes which I noted. It's actually 2 drowned roofs. One was a large one. The second one was a smaller one, which I paid myself. So you better talk to my wife about the budgets. That was really disastrous. I made strategic mistakes in facade designs by trying to sell facade systems to clients which were not really able to handle that. That's a risky pun. Timo, you will remember one of these projects. I once took a wrong phone call and didn't directly in the first 15 seconds react correct. And because of that, I never built the airport at Iceland. This is a true story. And I have one very brilliant friend, Thomas, you're going to bitch me on the bricks, who argues against me having a PhD in glass, that I'm now living in an Italian house out of bricks, which is an interesting story as well, and Thomas will refer to that a lot. So these are, say, my 5 mistakes I'm going to argue here. First speaker, Damien.
Your stage.
No Damien Rogan. Okay. Damien Rogan, he's head of facades at Eckersley O'Callaghan in London. The second last time we met was standing at the beach where Lisa Ramik was having her the celebration of her PhD with shoes.
Not the warmest beach I've been on.
Well, it was a Dutch beach,
Yeah,
and it was
Dutch
actually
beach.
quite okay. Well, I liked it.
Yeah.
That was really a
Memorable.
nice situation. He comes from the US, studied engineering at Washington University, a place I know as well. We never met, coincidentally, and then at some point he started working at Eckersleer Keller and doing all the facades. And since then, there's also some links into this group. They say, a clear focus for this engineering company doing all the glass things, now doing the glass. And now moving to this facade field. Yeah, and we talked about the mistakes, so.
Well, I'll try not to disappoint you.
Thank you.
Okay.
I like that one. Thank you.
All right. Thank you. Thanks very much, Uli, for the introduction. Yeah, as has been said, this was a difficult set of slides to pull together because we don't talk about our mistakes very often, and we upset our clients when we talk about them. So I'm treading carefully here and give you some truths, but keep some to myself. If you don't know us, as Uli said, we're a structural and facade engineering company. We have this middle ground, which is structural glass. I'll talk a little bit about glass because that's sort of our DNA of our company is knowing glass as a material very, very well. And we work very internationally. We have 11 offices, and we work in 30 different countries in a typical year. So this is, again, drawn from various places and various typologies of building. So I've tried to distill maybe not mistakes so much as truths that I've learned in our work. Truth number one, glass breaks. And when you're doing very bespoke glass projects, this is sometimes can be quite expensive to fix these. Glass can break for all sorts of reasons. Some you designed for, some that you don't, and you've got to be prepared for that eventuality, and it can be an expensive thing to fix. This is a retail store we've done for one of our clients in Sydney. This is when it's finished, but the day before, a week before it opened, one of these glass fins broke randomly in installation. And again, that's quite an expensive problem to solve when you've got to get a glass fin, 17-meter glass fin, made in Bavaria, chartered by a plane, Korean Airlines, to take to Sydney with several days to spare, closing a street to install that. Not something that you want to live with, but this happens. But glass breaks really is part of the learning. Now, we wouldn't be able to do such glass structures without a lot of testing, a lot of understanding the material, and that's cast glass, that's thin glass, that's all sorts of different ways that glass comes. We need to test that, we need to be comfortable with it, we need to design that if it does break, is it going to do so in a safe way, and that it has load-bearing capacity after it's broken. This is the nature of the material, and it's through doing such testing that you get comfortable with the material. You can then do such complex and eye-catching and daring projects as this, really, if you know the material well. And all of these daring moves that we've made with glass as a structural material is foundation of testing that we've done. Another project where glass breaks, as I think is relevant, is this 9-meter high glass tube facade, which we tried to do originally with shot glass, with glass tubes we were laminating together. Again, it broke. It's through this experimentation of trying glass, finding what can be made and what's just taking it too far, that it's the design process. It's through this that we select the materials, and we found that such drawn tubes that we tried to use wouldn't work. We had to go back to the beginning, back to flat glass curved into shape, formed into a tube unit, and then that's what's the realized project. My second truth is that renderings don't equal reality. This is something that we find is very much the case in glass, but also in stainless steel. This is a pavilion that we did with a structural glass supporting a stainless steel monocoque structure forming the roof. The beautifully curved rendering of the stainless steel is not quite as perfect in execution. But the second thing about this really is that the glass, we have glass is typically rendered as very transparent by architects. And reality is that glass does need coatings, it needs to perform, it's keeping the heat out. These spaces won't be comfortable if they're made of 100% clear glass. And again, a retail project that we've done, we take these beautiful photographs at night, but actually sometimes if you take that same photo in the daytime, it has a solar control coating on there. Maybe the problem isn't the glass, it's that there's too much glass. And I would say this is rich coming from me, from our company, but glass, there's such a thing as too much glass. Another project that we've done in London, where this was a bridge, where it's a 1970s, very famous 1970s building, where there's a bridge spanning over a road, and our architect and client wanted to fill in below that bridge with a very transparent, 100% glass, 6 meter tall, no framing. So no mullions on this glass, super transparent. You could see inside. It's going to be a market, food market inside. The reality is that too much glass, strong solar control coating, you couldn't even see into it. You've got to have a neon sign on the outside to tell you what's on the inside. And this is something that I think that we now are using tools, much more to understand what is the right amount of glass to use on facades. So we're trying to tell people, that is too much glass. It's going to be too dark. We're going much more through glass selection process to understand at an earlier stage what does the coating really look like, and through these small samples, not waiting until the end to design the structure and find the G value from the mechanical consultant, really tackling this glass selection head-on early stages. My third truth, don't know if I'm going too quickly or not, is that buildings need maintenance. This is a bit of a cheap one. This is a project that we did where actually I think that the execution looks better than the renderings. But the form of this project is that it's curved in plan. This facade is curving around a 120-year-old sequoia tree. Very important for the college. This is an Oxford college. Really beautifully executed by Frenner and Reifer. Mirror polished stainless steel, electroplated, curving around this tree. The problem is that tree has inhabitants, and very soon after, those inhabitants are leaving their mark on the facade. And this is 3 years later. It's pretty much caked in bird droppings, and it's not, again, what the rendering was promising us. And anyway, I'll leave that. Truth number 4, I've forgotten this now. Yeah, we like to make problems for ourselves. And, we're all engineers. We like to solve problems, but sometimes these problems are of our own making. This is a project that we've done in Shanghai with a pavilion. It's this pavilion in the middle with a concave roof. We were getting a bit excited with ourselves and made this a polished stainless steel roof. And then we find, actually, this project's in the press. Maybe we've got a similar problem here. And we got some really interesting analytical tools that we developed in order to solve this problem. But we then look around it. We have to do ray tracing of understanding where the sun is. Is that facade going to be concentrating the solar rays and projecting it onto buildings? So this is the analysis that we've done, understanding day by day, year by, throughout the year, how much it's concentrating the rays, finding that there is a problem. The inhabitants of that building are going to get melted, maybe. Finding that it's up to 20 times the incident radiation, the horizontal radiation that you would have found at certain times of day. These are relative, so these aren't absolute numbers, but 26 times the concentration. And then it forced us then to look at specularity, and we learned a lot about, it's not just about the reflectance of materials, it's about the specularity, it's about how light at the surface level is dispersed by the material. So we're learning a lot, and we've learned that by dulling down the material, and we tested different materials and find a solution that is maybe only 2 or 3 times the amount of radiation that they would have had on that facade, and everything is safe, no one burns, no one gets blinded, sealants aren't getting too hot, and it's a solution, but it's a solution to a problem that we made ourselves. My 5th truth. Yeah, this is maybe stepping back. It's a conversation that I've been having a lot in my last couple of days in Frankfurt. Yeah, we're very quick, I think, to demolish facades. We're doing half of our work now in office market is refurbishment of buildings. But refurbishment typically means keeping the frame, keeping the substructure, and replacing the facade. And often, that's being done typically not, maybe, this is a good example. It's just gone out of style. It's actually not because that facade is not working, it doesn't perform very well. It's just it's gone out of style. And really, we need to be thinking about this a bit more from a carbon level, because if a facade is making up about 14, 15, these are UK numbers published by Letty, they're typically about, say, 14% of embodied carbon of a building. But if you're taking if you ignore the substructure and the superstructure that's already there, that's kept, that facade is now making up maybe 40%, 50% of the embodied carbon of your refurbishment. And so really we've got to minimize that, and minimizing that is generally through reuse as much as we can of the existing fabric. And so this is what we're trying to do now. So one of our London projects at the moment, where we are keeping about 50% of the facade. We're infilling, we're replacing the glass, we're infilling with new triple glazing. We are refurbishing and we're extending the building, but we're really trying much harder to keep what's there, to prove that that it has a life left in it, and refurbish it where it's possible. This is a project that we've done in Paris, which is late stages of design at the moment, and only a certain amount of the facade is to be replaced. But what we found is that because facades inherently, they're a kit of parts. We talk about kit of parts as if it's a new idea, but unitized facades, we've been designing them as modular systems for a long time. So can we, with the new facade, maybe take what we're another side of the building, we're refurbishing all the center of it, but can we take some of those parts from the existing facade and place them on in a new place on the building, so that we don't need an entirely new facade? And we've looked at, so again, full reuse, partial replacement, full replacement. We're looking at all the different factors, looking at the U value, and again, the whole life carbon. What can be retained? How much that is going to change the whole life carbon of the building, and coming up with a matrix that justifies that facade is keeping about half of that facade and putting it in a different position on the building is giving us an enormous carbon benefit. And we've taken that even further on this project in Paris, where we've got an existing facade, 60 years old, coming to the end of its life, but a lot of that is salvageable. All of the aluminium components can be kept. We've cleaned them up, and we're putting them back on with new glazing, timber substructure, and able to put those facades right back where they were. And I've snuck in a 6th truth here, is that there's a lot that we still don't know. Now, I've got a couple of examples here, but effectively, the new environment that we're in these days, particularly around carbon, is leaving us in a place that I think we're starting back in the beginning of our understanding. Now, an example: carbon sequestration with timber. Now, we've got extremely different views on how that's accounted for in different countries, and as discussing this with Gertjan earlier, but it comes from historic reasons. It comes from maybe the way that our energy infrastructure is built differently in different countries, but our way of accounting for carbon is radically different. And although we're trying, there's just a lot of learning that we need to make. So the same facade maybe in the UK and in France, we get a completely different answer because of this carbon sequestration difference in our accounting. We get in the UK, it's a carbon positive facade, and in France, it's a carbon negative facade. Like we're still really scratching at the surface of how to account for carbon, embodied carbon, and yeah, there's a lot of learning to be done. This is again embodied carbon, something that we've started to build and calculate in all of our projects. We're at the case right now. We're getting pretty different results. I'm actually pleased. This is our calculation on the left-hand side here of a unitized facade. Modules A1 to A3, as in fabrication, and A1 to A5, including the transport and the works on site. We've calculated that, and we're getting to about 15% difference from what the fabricators' calculations say. I'm actually pretty pleased with that, but given that it's so poorly regulated at the moment, but 15% is something that we should be able to do better than. So again, we're still learning. We've got a lot going on, and when I look at the amount that we're trying to learn at the moment, these are all new terms to us. Over the last 5 years, and really this is the future of what we have to get to grips with as facade engineers to face the future. And yeah, it's pretty daunting. It feels like we've got the world on our shoulders, that we're trying to answer all of these questions. But this is where we are, and we've got to go back to the beginning and realize and admit that we don't know the answer to everything, and go back to school. That's it. Thank you very much.
So, glass is black.
Glasses still got a place, but
I remember,
only so much.
I remember, say, design exercises where we had the colleagues, the professors addressing to us, well, too much glass may be a point. Yeah. This aluminium facade, it's a 1 centimeter thick aluminium out of the 70s, 80s, isn't it? This one,
yeah.
For sure. So as say an aluminium or a facade lover, you really love it, you feel like, oh, you can't scrap it. So I get that point.
Yeah, but I mean, there's heritage and there's carbon, and there's good reasons to adapt keep this.
Yeah. Any questions to him? No questions? Come on, Thomas. You're the next. You're the next. You're next.
Okay.
You're next speaker. No, you come here. You're the next speaker. No, Damien.
Unceremonious.
Are you going to go to the same direction with the glass?
Yeah, I was happy. Happy to hear to hear your direction, because at the beginning I thought my question will be, did you ever look into embodied carbon of glass?
Yeah,
and so on. So I'm really happy that he talked about what is the adequate level of glass.
Yeah. It's fundamental, I think, to all of our projects now. We're asking this, but and reuse, and we're in Vicona's studio today, and there's big advances, I think, being made in embodied carbon of aluminium and recycling and take back. We are doing that in glass. We've got 3 projects now where we're taking back the glass, but still to be crushed and made into new glass. Not so much reused on another project, but that's where we'll have to get to.
That's the next research.
It's the next research.
Cut off on.
Thank you very much.
Okay. First of all, thank you very much for the invitation. Love to be here today. When Uli called me, gave me some headaches, I have to say. Talking about mistakes and errors, it was, let's say, hard to get around. So I had my same problem you had, and I like the word you find, the truth. Like I called it the critical reflection. So that was my workaround, the problem. The second workaround was that I have chosen projects where we have no liability anymore. So all of them are very old and nobody can sue us. So that was my 2 workarounds. And I didn't find 5, I found 3 projects. Sorry, Uli. 3 projects where I have some critical reflection about and some minor mistakes in between. Okay, so this is how I built it up. So, I mean, you talked about, let's say, how can I say? Let's say the complexity, the amount of glass, etc. This is what we have seen a lot. I think we all know that we need to decarbonize the building sector. And how can we achieve this? And we see a lot gadgets on buildings, and nobody talks about the thing. But this is, let's say, the philosophy of the last decades. Architects came up with, let's say, there was always this issue about the freedom in design. And engineers tend to make it work. And so together, we made things more complex to solve the solution. And nobody asked about the thing. Nobody asked about the hammer, which is stupid to begin with. And I think that's exactly what you said now. Things are getting more serious. We talk about embodied carbon, we talk about serious decarbonization, and suddenly we find that a lot of these, I would say, hero architecture, these big architectural gestures of the last decade, we bought with an enormous use of resources. And this is not appropriate anymore, and that's why we need to reflect and be critical about the thing. And so this was always our philosophy. We have to achieve performance by design. And now I jump back something like almost 30 years. One of my first projects was actually here in Frankfurt, Prisma with Auer & Weber and partners. A project I still love. I still kind of adopted it. It's like my baby. They renovated now, changed the natural ventilation. But when we started, we worked with Auer & Weber on the competition already. And because the environment there in Niederrad is not so beautiful, everybody had the idea it has to be, the building has to have its own inner world. It was designed as the Hochtief headquarters, Southwest headquarters. And so there was this big atria, but then Hochtief put into the competition brief that they wanted to have a naturally ventilated building. So now, how do you manage such a big building with an atria to be fully naturally ventilated? And so this was the same thing, like I felt challenged as an engineer. Do we find a solution for this, like mission impossible? And so in the competition, we already got to the idea we need to somehow cross-ventilate this building. And there can be partition walls so that we have offices facing the outside and we have offices facing the atria. And by code, the office facing the atria is an internal space which needs to have mechanical ventilation. So that's the code. So how do we get around the code? And then because of the, how is it called? The big street there in Niederrad and the noise level, we proposed a double facade towards the south, towards the street. So we made it as complicated as possible. I think you start to recognize. So that was the idea then. We said, like, what if we have ducts embedded in the concrete slab and we connect the office facing the atria to the double facade space, and we connect the space facing the double facade towards the atria. And so in the atria, we have a chimney effect, and in winter, the air from the atria is warmer than the outside, and it wants to go out. So we get a chimney effect in the atria, which pulls air through those ducts, let's say through the space from the double facade through the building. So we can have, despite the partition walls, we can have natural ventilation in winter. So that works well. But then So here you see some examples. We won the competition, by the way. I forgot to mention. And there was pretty funny, like when they called and said, you won the competition, we were all like, oh yeah, we won the competition. And the second reaction, oh shit. Like during a competition, you think it's all fun. And then suddenly then the client came in, Hochtief, and said, you promised a pretty innovative building and a beautiful design, but we want you to design this building as you have promised in the competition. At that moment, we recognized this. Now it gets serious. So they built it. They put there was a lengthy design process, I have to say, and it was also going through a peer review process. They included the TU Dresden, and it was Hochtief was really supportive. I have to say, it was a really nice process at the end. But we ended up with all these ducts. Here you see it being embedded in the slab, in the concrete slab, to create this cross ventilation. So to continue the story, now in summer the double facade is getting too hot. So we said then we shade the whole glass atria from the outside and then use the double facade as a chimney that runs all the natural ventilation, and we have a ground duct to pre-cool the air that goes into the atria to keep the atria cool, etc., etc. And then reversed the direction. So that was the idea. Okay, and then here you see the ground duct, the louvers, how we shaded the glass roof. Here you see the glass roof being unshaded, and then in a shaded state, partially with the louvers that redirect also light in winter towards the trees, because there was supposed to be trees that needed to get some daylight to grow, and for the other areas we had a fabric that shades the roof. So this is the double facade, one of the early double facades on big buildings in Germany, and so we were super proud. We had some issues, I have to say, during commissioning and then monitoring of the building. The first problem, the trees died. Pretty expensive trees from Argentina. The reason was there was a signal during Christmas break and the smoke exhaust openings from the atria opened and there was nobody recognized, and so they got temperatures below freezing in the atria, and so the trees died. Some of them recovered, but it was like typical control issue. We had several control issues in this building, just to list some of them. No central control of shading devices due to hardware issues. Took them a year before they recognized it. A year just to recognize that the shading doesn't go up and down when it should. Then permanent signal instead of an impulse. Sensors show wrong numbers, like you needed to check every single sensor. Is the number correct? Then wrong sensors or incorrect installation, like temperature setting sensors getting sun exposure, then it shows a wrong number. Some sensors' position got lost. Nobody knew where they are. The most funny line item I found was sensors show reasonable numbers without being installed. They showed the correct numbers, but we're not there. Haven't been there. So all of these things happened, and it was a really lengthy process. And we had access to the BMS from Stuttgart, from the office. We looked into it, and at some point, we had over 30 degrees, sunny day here in Frankfurt. And the shade of the roof was not closed, and then we called the maintenance people, say, hey, something is wrong with the BMS. And then they were sitting in a basement in a cockpit with like 10 monitors. And so they checked their BMS, and they said, no, it's raining. We said, come on, guys, go outside. It's not raining. It's a super sunny day. So what happened is a spider was like building a net inside the rain sensor. So over weeks and months, nobody recognized the problem. The shades did not close. So all these issues we had. Then the bigger issue was, oh yeah, that's not important. What happened? Sorry. So what we recognized, commissioning, but also monitoring, is a must for these buildings. It's not a nice to have. Those buildings, these kind of buildings where we want to use passive strategies that are, let's say, in line with the mechanical support here and there where needed, like supplemented by mechanical systems, highly glazed, they need time to operate properly. They need, and that's not common. And we know, let's say, performance gap is a big issue. We talk about today. There are studies published that show that modern office buildings in Germany do have a performance gap somewhere between 30 and 70%. Modern office buildings. That's usual. That's what we have accepted, which is incredible. And commissioning needs every single flap here. You need to check. You need to check: does it open? Does it not open? When does it open? Etc. Etc. It's a huge amount of work. So something we need to critically reflect. And then the user, what happened is that a bank moved into the building. So it was designed for Hochtief. And then Hochtief got a good, let's say, offer. So a bank moved into the building. And they were quite unhappy with the building, I can say. Now they moved out, I think I can say it now. And one of the reasons was, we did modeling, we showed Hochtief that in summer they're going to get 29 degrees in this building. There was no cooling in this building, in this highly glazed building, no cooling, just passive systems. And they put in a contract with the bank, a maximum temperature of 26. So the bank said, the building does not work, there's a design error. Now, the building owner said, the performance can be improved, it just takes some time. That's what the building owner said. The designers, like we said, the building does what we promised if all systems work correctly with all the problems we had. But in those areas where we showed where the systems worked correctly, we could indeed show that the building does what we promised to the client. And then the contractor said, we installed what you tendered. So it all was going in a circle forever and so on. But the first critical reflection is, it's not about the design error, it's not about failure, but the building is indeed too complex. It's a pretty complex building, having, let's say, with all the ducts, having a flap on each duct, controlling the natural ventilation, depending on outdoor conditions, on wind, on temperature differences, and so on. And you need to change direction. And try to explain this to maintenance people, to facility managers, and they sell the contract every 2 years to a new company. That's the truth, like coming back to the truth. So that's what we need to reflect. It's too complicated, too many building management system control movable parts in this building, which we need to control. So that's my lesson learned. We have to get to simpler solutions. Then, Uli, you're surprised. A project we did together, it was the first time I met Uli, 25 years ago, almost 25. For Debitel, a cell phone company, I mean, everybody might remember Debitel, their headquarters in Stuttgart. And we had this idea to run ventilation, let's say a natural exhaust by this solar chimney. And having heat recovery with a solar chimney is quite complicated. In the meantime, by code, it's required to have heat recovery when you have mechanical ventilation. It was not the case at that time. But they designed a computer center under the building with 600 square meter and huge internal heat loads. So 24/7 all year long cooling demand. And so we argued, why do we need to build here a complicated heat recovery system in a naturally ventilated system when we have so much waste energy in this building? Why don't we just use the waste energy from the computer center? So what happened, just after they moved into the building, they got bought by Orange, and the computer center went to the UK. It was never built. There was never waste heat in this building. We operate the building for 20 years now without waste heat and without heat recovery. So what we do is, as a critical reflection, we tend to tailor buildings to current needs, to what we know. But the buildings, they last much longer. So how do we know what's going to happen in 5 years, in 10 years, in 50 years in a building? Can we really tailor to very specific needs at a specific time? In this case, we tailored it to conditions which actually never happened. Is it a design mistake? It's not a design mistake. I mean, we told it the client, but it's still wrong. So just again, it's a critical reflection. Now coming to another project, and I have to say, I'm still proud of all these projects I show here. Just there are aspects which I would do differently today. It's Winnipeg, Manitoba Hydro, where we work with KPMG architects. Winnipeg, super cold climate, minus 35 degrees in winter, and we designed this kind of climate responsive building where we have south-facing winter gardens we use as a solar collector to preheat the fresh air we distribute through the building in winter, going down in a heat recovery system in this case. Here we built a heat recovery. But then in summer, when we don't need heat recovery, we have this chimney for running a natural building exhaust. We have these HR, this is the solar collector. This is the mechanical system of the building. This is the mechanical ventilation. All the units are under this bench to the right, and then the units which take the air, which is then heated up by the sun, and there is a water feature in the background you can barely see, but the water feature provides the humidification. So it's a whole air treatment system, the whole winter garden. We take then by units which are placed behind those panels to the left and distributed by a raised floor plenum into the depth of the floor plate. There's a double facade to the east and to the west. It's pretty windy there, so we have the shading device in the double facade. It's weather protected. We have natural ventilation. We have a radiant system for heating and cooling in the slab. And I want to talk later quickly about the radiant system, because what they told us in design is it's all going to be open space. And if there will be individual offices, they're not going to be on the exterior facade. Because as soon as you put an individual office on an exterior facade, it blocks the light for the others. So it has to go to the core. Along the facade, it will all be open space. So remember that one, because it's going to be important. So this is the floor plate. Then, so it's this V-shaped building with the HR facing south. But what you see already is individual offices on the south tip. And there is no shading on this south tip. We have shading along the long sides to the east and to the west, where we have the double facade, but not on the south tip. In our modeling, this was basically one open space. No overheating problems, because we can solve it by the depth of the floor plate of the slab, which we use for cooling purposes. But now if we have suddenly a small space with fully glazed to the south, fully glazed with a double facade to the west, we do have an issue. And so what happened is, like, all the department heads, they found that this is the most fascinating, best view. Let's say this all-glass corner is the, let's say, most beautiful space. And they all said, like, I want to have my office there. And we were running into an issue. Again, was it a mistake? We could have, let's say, expected that this is going to happen. But it was at the end, nobody sued us because they told us it's going to be an open space office. So it was at the end not our, let's say, not a legal problem, but I still find something we should have expected, that it's going to happen. Now, coming back to the good part of the story, energy requirement, MNECB was the Canadian code at that time, and the 88 kilowatt hours per square meter in a year is what we modeled. And then it took us 2 years, again, doing monitoring. And the building is by far not as complicated as the Prisma building here in Frankfurt. But it took us 2 years to get the building to operate as designed. 2 years. And this is something usually nobody does. And the performance gap the first year of operation was almost 100%. The building used almost 100% more energy than what we have projected in design. So that's the one lesson learned. Let's say those buildings where we have, which are, it doesn't matter, sorry. Those buildings which are highly glazed, interactive, adaptive facades, passive systems, supplemented with mechanical systems, they're complicated, and you need to fine-tune those buildings. And not only those buildings, also buildings which are has a fully mechanical systems, which are fully air-conditioned, they do have the same problem. They need this fine-tuning, they need this commissioning, they need this monitoring to get them to work as designed. And again, but what we saw at the same time is that, let's say, despite this amount of glass, it can be very energy efficient. It's still today published as the most energy efficient high-rise building in North America. It's 15 years old, which is a shame in itself. But it's still considered the most energy efficient high-rise building in North America. And because of this, everybody who is ambitious in North America knows this, ambitious in terms of sustainability, knows this building, but nobody copied it. Google was there, Apple was there, looked at the building. Nobody tried to copy the idea of climate responsive design. They all ended up with, let's say, their typical all-glass buildings. And this is an image of Dubai. This all-glass buildings, now coming back to your story, we used too much glass in a way that doesn't make any sense. We showed the world that we can do smart glass buildings, but the world is copying stupid glass buildings. So as a third critical reflection, glass and high-tech architecture has failed as a role model. I think that's the point. We built lighthouse projects and expected the lighthouse projects to become role models, but if nobody copies those projects, it's not a role model. And we have seen they are sensitive, so they're also not robust. So all this fine-tuning, etc. So they kind of failed as a role model and in terms of robustness and sustainability. And this is, let's say, where we have to become better. Now I've talked about a couple of reflections and a couple of mistakes. I think we might continue. Yeah, we might get into the fight. Thank you very much. Now coming to your brick building.
Yes, go on.
No, you go first.
So why did it not happen to be a role model? What are the reasons?
I think, first of all, I think the building industry is conservative. I mean, these are expensive buildings. You need to be brave to say, I invest now a couple of $100 million in something which is considered an experiment. So that's number one. By the way, people are very happy. So we have comfort data, we have sick days, statistics, and so on. And it shows that it works extremely well for the people. Second problem, coming to double facades. Double facades, they have a depth. Look at Canary Wharf, banking district in London. The square meter ground costs a fortune. If you give the facade depth, you lose floor square meters, floor area. And this is a no-go. So that's why we end up with stupid glass facades. No depth, no climate responsiveness, no opera window, no external shading. Everything we know how it works, but nobody does.
Quite talking to the facade people here.
And then you end up with the black boxes, because then you put the coating on glass to fix it. And we end up with a building which is not what we promised in the rendering. Yeah.
So we quote you with less glass is more.
Yeah.
Check. Thank you.
You're welcome. Sorry.
Here comes another glass friend.
No.
We actually both did our PhD in glass. I was giving a speech and you were arguing against me.
Oh, that old story. That old story.
Things changed.
Yeah.
Off you go.
Yeah. When Uli asked me to have a speech about mistakes, and then fortunately he said, but the theme will be, and the truth is. And though I had the whole weekend to think about what is the real truth. And I would like to start with some kind of chronology. And I would like to start with the first one. Unfortunately, it's again into the news. It's this Chernobyl sarcophagus, 1986. There was this huge collapse, this chain reaction, the largest catastrophic we had in the worldwide. And I need to start with this because at that year, that's an estimate, if you go into the internet, it's an estimate that about 100,000, up to 100,000 Soviet armed soldiers that die during the balancing of this catastrophic reactor, of this burned reactor. It took about half a year, and after that half a year, they built up some kind of shelter. And that was already in 1968, and since 1992, they were asking, they said, okay, this first shelter, which had been built up with huge demands of personal death, this will release only for 20 years maximum. But actually, after a couple of years later, it starts collapsing. And that was an international asked question. So in that time, in 1997, there was built up a shelter implementation plan. What are the demands to get a long-term safetiness to that reactor? In 1998, so 1998, that's the truth. Actually, that was a question how to talk about. At that time, I was working as a young engineer in Hamburg in an office. Joachim Klint, he came to that office. Joachim Klint, he was a fire engineer specialized on fire protection issues in atomic reactors. And he came to the office and said, I have been to Chernobyl because we there had demands and they had questions on that. And all what the world and the engineers and companies worldwide do at that time is completely the wrong direction. There are complete different ideas and items we have to provide. And then we started, my boss at that time said, let's talk with them. As long as you do your projects are running, you can do it. And we sit together. And that was just this, we call it right on brainstorming. There was a guy from a different company with complete different ideas, and he came with us, and we brought it together, this ideas, and I said, okay, it's not a way how the companies did at that time to concrete any big blocks and walls and slabs and ceilings on top as they did it all the time for any other reactors. We have to do it quite different. We have to protect the rain and the dust. And we have to do it to build up a tent a certain direction outside. So at that time, we built it up. We went with this idea. We did calculations on that. We went to Kiev, to the government. We explained them that their specialists are completely on the wrong way and said, that's fine. Then, fortunately, we did even some publications. We were on a congress in Moscow, even to explain to the specialists what needs to be done, what is to get this shelter in the right direction. Afterwards, Joachim Klint, he even got in contact with German companies, with international companies. He said, oh, that's fine. And then we heard nothing. Fortunately, we claimed the idea. That was in 1999, 2000. 15 years later, he called me. He said, have a look at the news. They published it, they finished it. And then in the news, this is the new safe commitment. They designed it, they built it up, they had the money, they got the money. And other companies, which we talked in first years before, they did it. And that's the truth that actually it's exactly the same idea. They built it up. It was a little bit more heavier than the compartment we designed in 1998. And that's the question, or the resume of this afterwards is we as engineers or architects, we are going to invent all day. We create ideas, we create possibilities, as the two other guys already mentioned. And we have to claim for this. If we would have lawyers, we would even fight for our ideas, to get involved into the project, to get paid for our ideas. But as an architect or an engineer, we are maybe too lazy or even too naive. I don't know. That was maybe the first idea where I said, okay, this project, the largest movable project building ever built, 110 meters in height, 260 meters in span, and 106 meters in length. Actually, the final one has about 36,000 tons of steel, and we estimated 15 years before with 22,000 tons of steel. But the idea, all the stuff was the same. So maybe this is my first idea how to deal with the question, and the truth is. So it's really the question for us all, how can we really claim for our ideas and fight for them? Next point, that's the glass one. The Nordkettenbahn is, I guess it's very well known. There's 4 stations of Facade in Innsbruck. And in 2003, an Austrian company, general contractor for these 4 stations, asked the office here in Frankfurt, Bollinger and Grohmann, could you support us? And then the question was, how can we do it? And because there are about 2,000 different free-form shaped glass units, and that was the first steps of Rhino and all the other 3D files, where we even just tried to organize how many forms and how many curvatures, how many radius should be mentioned, how many elements should be calculated, and how do we get an idea to fix those elements to the steel structure in below. So 4 different stations, and I took this project out because I was with students last summer, still in a fine condition, some maintenance, so they respect the building and the quality of that building, of that 4 buildings. And but the question was always, how can we manage to fix them? And as you see, there are no joints or any screws, anything else. It's just a glass plane on top, on below, on the side. So there was a question how to do it. And I bring this story or this project because when I presented the first time the presentation in 2005, about 15 years ago, in a conference in Dresden, there were 150 glass experts, and I didn't even finish my speech because they were shouting. How can a German engineer ignore German regulation on glass design? What is about post-breakage behavior and all that stuff? So I didn't come to the end even to explain what we did and how and what is the safety perspective or system behind this towards this element, because each roof consists of a steel structure, like a bone structure, with a lot of different shapes. So it means every of these ribs has a different shape. So how to fix a glass on so much twisting geometry? And that isn't a long term of design where we said, okay, sitting together with a contractor, he had said, okay, very easy, we glue it and then we just bring it to that end. After 1 week we asked, how often does the glass surface really fits in a rectangular shape to the rib? How often? Once. So we have to consider. Then we started, okay, we will do it as we find it in other sections. It stands after we even thought about the power joint of a surfboard, how to fix it with this one. But it was always a question, checking the total geometry, not of one, of all stations. We always came to an end. It needs to be much more easier and it needs to be much more flexible. Well, at the end, with the whole story, a lot of aluminium profiles, screwing devices, additional ones, we came to the end. We need to have a 3D melted profile which could be connected directly to the steel rib, which could be easily be screwed by a steel plate, and this steel plate is glued with an adhesive layer to the glass. That was a moment where they all asked, are you crazy? And at that time, I wasn't able to explain it further on. So in principle, we have those profiles. It took a lot, weeks to design all those different profiles. And it took about 1 week to create them, to build them, to melt them out. And then we had the mock-up. So just one of those elements where you see the different profiles, the plastic profiles, and already you see here these elements. And the question was how to bring a similar safetiness to the structure. Not the question, how can we directly fulfill all paragraphs in a code. Fortunately, it wasn't Germany, it was in Austria. And it was a project of national interest. So the question was how to do it. The first one was the glass producer was not able to do laminated glass. So there are always single plane glass elements. How to reach this post-breakage behavior. There the contractor, the managing contractor, he went to China, anywhere to China. He never explained and told us where he found the company. And they had a special film, very toxic, even after months of transport. When they unpacked these elements, it was crazy, it stunk. It was a horrible smell. So, but this element that they tested, this film in combination with the glass, did even fulfill this post-breakage behavior. So the first item was solved. The second one was, how can we glue those elements to the glass, and how can we provide those elements, those small strips, to the steel structure, or even to this plastic fixation, to the plastic edge elements. And then the question came up: gluing, structural sealing glazing, regulations. They are all very not conservative, but they are produced or even installed for a certain amount of glass. And we said, okay, we have a lot of individual glass element fittings. And actually this was just a small idea to say, okay, every second gets a thicker element. So in a normal, and even since 15 years, every second of this individual fixations is just fixing the glass to the steel. And the other 50%, they will just come into action when the first 50% will fail. That means the glass will fall down for some millimeters, and while this element, the structure is maintained, you will individually see that the origin performance of this sealant will fail. So we have a checkup It's always combined with a maintenance. But if we want to start with new ideas, we have even to think over the whole range. What can we do? How can we check? And how can we even involve the maintenance, the owner, the clients into such buildings, into such solutions? So this was tested. Everything was fine. It took a lot of years, of months, to get even the approval by the Austrian authorities. And then the real question was, what we didn't check, was a question of logistic. How many of such profiles need to be melted just for one rib? So it works. It worked perfectly, but it has even the, let's say, the limits of warm bending. You see those joints, they are not perfectly. And then, I don't know what, when Zaha Hadid was there for the grand opening, if she saw these joints or not, but until now, everyone is happy. What I want to mention is, the truth is, we should, in the beginning, ask, is it the right material or the right design for this purpose? This question had never been asked, whether from the client, from the general managing contractor to the architect, nor from us to the company. Is it the right material for this solution? We found a solution, an engineering solution for this, but the question is it correct? So, next one. And I call it the exchange between planning and construction. This is typically construction site, a lot of steel, a lot of working and on the construction site. And one day when there was a slab was already concreted, the foreman, he called me at 6 o'clock, I know exactly. He called me in summer and said, so we are finished with the concreting, but we have a lot of those double strips left over. What happened? I said, are you sure? So we immediately checked. I said, wait, we used all the reinforcement plans. We did it properly. And asked, did you have a look on the formwork plans as well, where all these double strips had been even laid out? Of course, on the plans, there is a signature and information that you have even to check both plans for the realization. But it needs to be even talked about that. So I asked him, I said, I guess they are missing. We stop the phone call right now. Call all your workers. The concrete is not that hard at the moment. Take all these jackhammers you have available and take out the concrete again. It would have been a big mistake, a big disadvantage, a big risk for the building. It's just a question, and we write it on plans, we write it on descriptions, but sometimes we miss to talk about something. We have to explain, as engineers and architects, what we have in mind. And it's not sufficient just to write it on a plan or on a forward of a document. So we should imagine that there are people on the site working night and day at all climate conditions to realize this thing, and mistakes can happen. As said, and that's the last one, it's a very small building, apartment building, high insulated bricks, masonry bricks, and there is, of course, an explanation how to handle those bricks. And the architect, he called us and said, those bricks are cracking more and more, and you see there's something like these elements are cracked. The whole building starts to collapse because the bricks, they didn't work. And it was a very simple idea. So we had to suspend the building, the slabs, from the top floor to the basement, the whole building. And of course, we had even to take out those elements, those strips, in every level, and to replace it by a concrete column in the wall. And the question was over here, that's the Verarbeitungshinweise und Planungsempfehlung. So every foreman on the construction site should read it, should be aware. It's written in the plans, it's written in the architectural plans, it's written in our plans. But what is a foreman? He said there should be a small styrofoam strip at the inner edge of the slab. What did he think? Okay, I have so many styrofoam. I take in the whole depth. And that happens that even out of the slab and the turnaround of the slab, these elements here, they start to crack. So those Verarbeitungshinweise are necessary, but we need the conversation between planners and construction companies. Otherwise, we could have a lot of fine ideas without any realization. Again, exchange between planning and construction side. I'm not talking again about this Nordkettenbahn. But if we have this in mind, that we are not willing to think about all these ideas we have in mind, and we should talk about the plan issue and the construction. This is a comic strip out of the 70s. The architects and the companies, they are designing and talking about what to do. This small worker on the plan, he just claps the fly. Everything is fine. They never talk about that, and that happens afterwards. Thank you very much.
So 2 questions. First one, how would you overcome this communication problem?
I think our services, we should be more involved in the realization process.
More at site.
More at site. But the clients, they are not willing to pay for that. It's a service which is not for free, which needs a certain...
You have it in the Honorarordnung. So
the Honorarordnung doesn't has any idea, from my perspective, even to realize it.
Okay, more on site. And second question, how would you do Zugkettenbahn in a different material? Shiny, whitish.
With polycarbonate.
Polycarbonate?
Yeah.
30 years?
Yes.
Surface?
Yes.
Okay, we keep it. Thank you. Next speaker, Rob Neisser. I'm very happy that he's here. I remember very well that he had this single-layered curved glass in Antwerp, and I called you at one time, and I was a bit frightened about it. And he was super cool and relaxed. Oh yeah, the forces found their second way to go down. It's also, say, a tricky one. Rob was a colleague in Delft, in the civil engineering faculty, as well as in the architectural faculty. He was a partner at ABT, a very well-known Dutch engineering company, and he now supports one of our PhDs with an, say, art engineering company. Yeah. And I remember lots of talks of you. Are you going to show the Hanover thing?
Yeah, no, we don't.
Okay, I'll ask that
There
later.
were a lot of mistakes in there.
Yeah, I asked that later. Okay, off you go.
Okay. Well, the word not to be mentioned today is mistake. But we all make mistake every day. Yesterday I was driving over here on the beautiful Autobahn. I was driving about 150 per hour, and then suddenly there was flash. There was a 100-kilometer zone. So that's a big mistake. It will cost me money. Yeah? But it proves we all make mistakes. And we make one very big, the biggest possible mistake, if we don't learn from these mistakes. And that's that's how I looked at this. You must learn from your mistakes. You must be able to say, okay, I made a mistake, let's find a solution. And don't go to the client or to whatever is doing, the architect who is responsible, and say, oh, I made a mistake, I don't know how to solve it. No, you must come, we made a mistake, and this is the way we're going to solve it. That sounds very easy, but it's the hardest job you can do. But I'm here to tell you of my mistakes and the way I was finally able to control them. I don't talk about the mistakes in Hanover, because I didn't solve them. Yeah, deteriorating, yeah. Okay, we're going to talk about curved glass facades, and I want to explain you something. Let's go to the next one. One day, the famous Dutch architect Rem Koolhaas called me up. Come to my office immediately. I have something to ask you. I worked with him before, and he knew that I was a glass expert, expert in structures out of glass. And he said, we've won this competition, and we have a big window overlooking the city of Porto, and I want only glass to be looked at. No steel profiles, no nothing, only glass. And you have 1 week to come up with a solution. And then he was gone again. And they said, oh, I have a team of people who will help you doing it. Well, we started working. Small profiles, glass fins, glass boxes stapled up, etc., cable nets. And then we presented it on a Friday to Rem Koolhaas. And he's very quick. He said, nothing. Impossible. No, okay. Nothing. He says, is this all you could think of? I said, well, I had a sleepless night before because I know I had no solution. And during the sleepless night, I thought, wow, one thing I have forgotten. I saw an ad in an advertisement for shop interiors. Shop interiors are very nice to look at. Why? There's no wind. There's no rain, so they can make anything. And I saw one shop in Spain with a fashion shop with a woman department and a man department and a curved glass wall standing on the floor inside. And I saw that and thought, oh, that's nice. And then I forgot it, and then it came back. And why is that the solution to the problem? Because if you take a piece of glass, like this piece of paper, it doesn't work. If the wind blows against it, it will deform. But if you take the same panel of glass, and I have to do it very carefully, and you fold it over a few times, which I learned at kindergarten, but now it proves to be difficult, and suddenly the same panel of glass, same material, is very strong. And you can put them straight up and say, this is the facade. I told it to Rem Koolhaas, he said, okay, let's do it, and gone he was. So we had to solve and try to work it out. But I always loved this experience, although I had a sleepless night, but suddenly the solution was there. And here you see the result. And the architects love this. They say, the reality is deformed. You see reality, but it's deformed. Wow. And they would talk about it for hours. But here you see my problem I present you. Thick line, small line. Holger has showed the same. Thick line, small line. We even had lines like this. Problem. And the architect says, when it was realized, we don't like it. You should change it. Can you do it better? We improved a few things together with the company who made the glass, the curved glass, a very good firm from Barcelona, Cricursa, and they were able to change a few things, but they couldn't control the company problem. And finally, the architects accepted it, and it was not an issue anymore. So we have this beautiful structure standing there. And now the architects start to philosophize if it's finished. And they have this philosophy of the old Greek people who say the world is built up of 4 elements, fire, air, earth, and water. And here we have all those combined. Here the image at night, Also beautiful. And here you see the philosophy of the architect afterwards developed. They say, we have the water in the glass. We have the earth in the concrete outside. We have the fire of creativity inside. And we have the earth, the water, earth, air. Now, the air is always there, so that's not a problem. So, so they were starting all the new film. But I like this idea that the glass is not a plain, is it black, is it transparent, nobody knows. But now it's water. Yeah? So the answer to the question will be glass is water. Okay, then the next project in this curved glass, because the architects love it. Wow, curved glass. And so sustainable. You take a 12 millimeter glass panel, you deform it, and it is very strong, very strong. You are very efficient. You're very sustainable in that. With the next architect, we start making design for a museum in Antwerp. And we said, well, how can we avoid the number of joints? Yeah? For we had this lesson learned from Porto, it's going to be difficult. We said, well, let's not make a C joint, C joint, C joint, 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 joint. Problem, problem, problem. Let's make an S shape. Factory, can you make it? Yes, they said we can make it. And we only have one silicon joint. So we started to work on that. And then we were talking to the company who make those, and here you see an image of the design of the building. In Porto, we had 4.5 meter high glass. Here we have 11 meter high glass, because we could make 5.5 meter long glass panels, and we could put them on top of each other with 11 meters, which the architect loved because you have a corner and look out over the city of Antwerp to his deformed reality. So we started talking to the company, how can we make it, how can we make sure that everything is straight and red? And I'll tell you the secret later. Because first, another lesson we learned from this problem. Here you see the computer calculations of the glass. And you can see that this shape is stronger than this shape. That is reality. Why is that? Because we have a big tensile zone here, if the wind comes from this side, and a small tensile zone here. So it deforms more. You can see it here in the color red, 8.6 millimeters, and here it's 5.4, 4.3. So it deforms in a different way. That was a lesson learned. So we started talking to the company who made it, because there was already then the design files. And we had a lot of questions, because in Belgium, you deal with the insurance company, who must say it is a safe solution. And in Belgium, they have a lot of inspectors running around, looking at mistakes like Holger showed, that he put cement inside the joint instead of polystyrene. I think that's one of the solutions. There got to be supervisors on site which checks everything. And that costs money, yes. But how much cost the mistakes? Oh, everybody forgets that. So the insurance company said, you make beautiful computer calculations, but how will it be in reality? Can you prove it to me? I said, well, we can. We may simply make a test. You tell me which load I should pay it. So they say twice the highest possible wind load according to the Belgium standards. So we put it on in the factory. We have here the curved glass, the S-shaped facade. And here we have 2 times the Belgian biggest wind load on it. And it survived without a problem. And even almost secure, the deformations measured were equal to the computer calculations. So that's a very important point. How do we check on the shape, that the things would not be deformed? Because it's warm, it's melted over a mold. So we had the people from the factory say, we make this, we called it a letterbox, where you put the letters in. So. And they put through the whole glass panel, and if it passed through, it was okay. If not, it had to go back to the furnace to be heated up again and to be corrected in the same shape. So this is an important thing I'll show you. How do we put the glass on top of each other? Simply, panel 1, steel element, panel 2, collect the connections. Here they can move, because don't forget that in a facade, you have the sun burning on your facade, it will expand, and in the winter, when it's very cold, it will shrink. So all movements must be possible. The deformation, both in the horizontal plane and the vertical plane, must be possible inside the details. And here you see the result during construction, and here they're working up. Everything has to fit. It's always very difficult, and sometimes it fails. And sometimes things are broken during transport. It's always, to work in the building industry, it's not a nice job. But the architect liked the concept, and they say, wow, we've won a competition in Qatar, in Arab. And they say, we give the water back to the desert. Yeah, okay. It's completely foolish to build a 70-meter high facade, 80-meter long, in Arab, in the desert. We had to do a lot of difficulties, a lot of things to solve. Thank God air conditioning and cost for air conditioning was not a problem over there. So they don't care. We had to put a lot of dots on the glass to reflect the sunlight. The architect wanted to have them in silver. Even the Arabs couldn't pay that, so we made them white. And we also had to take care of this. We had not severe earthquakes, but we had earthquakes. And we had made a building without any diagonals in it, or walls, stability walls. So we had to move with big columns which move around during an earthquake. So, oh, you have to make deformations of about 3 centimeters in the facade. Well, we thought about that by making a special kind of joint here, which could take up, like you can see here, the movement of the building. And also here, the deformation is possible in the vertical way. Shrinkage in the night, it can be 0 degrees over there. An expansion during the day, 50 degrees, which is unbelievable, but it happened in one day. It has to breathe, the whole building has to breathe. And that must be possible. If you try to block that, the glass will crack. This is not a good drawing, but I have no better idea. The whole facade is hanging from the top. So we have steel bars going through, which hold these horizontal profiles which take up the wind load. And on top of those profiles, we place in between the insulated glass panels that we have made. On top, we have a hinge, but not 1 hinge, but 2 hinges. For if 2 hinges move, it will always be straight. If you have 1 inch, it will go like this. If you have 2 inches, it will go like this. Very important detail. Here we have the possibility to expand and shrink, but also to take up the horizontal wind load over here. So we have a special detail over here to take up this horizontal wind load. Next project, we have another project. We also have a beautiful glass facade. I'm not going to tell you much about this one, but look at the railing on top, which is also curved glass. And we had to do a lot of tests over there with heavy weights being smashed against it. But as you know, this is very strong. And if you have a good top connection made and a good bottom connection, it can take up easily those enormous forces up to 3 kilograms. The crystal houses, as they were called after a few times. We have a lot of crazy architects in the Netherlands. And one of them is Winnie Maas of MVRDV. And Winnie Maas had got a commission for an expensive shopping street in Amsterdam, near the famous museums we have in the Netherlands. So a lot of Russian people, not anymore, were coming there. And Chinese people and Arab people, and after they've seen being a culture, they have to buy things. So we have these beautiful shops. And one owner of 2 or 3 buildings wanted to do something special. He said, we must do something extraordinary. And he gave a commission to Winnie Maas to look into possibilities. And Winnie Maas had sleepless nights, he said to me. And suddenly he had the idea to take the original design from the 1890s, which was a brick building, to build it completely in glass. Glass bricks, glass windows, glass doors, everything made out of glass. And he came to me and said, Rob, can we build it? Okay, here we go again. Yeah. I say, yes, we can. I was working there at the university in Delft, so I had a big laboratory at my disposal. And they said, but we must do a lot of tests in the building, and it will cost the client a lot of money. And the client, he saw this beautiful image. Here you see a night image, and also had the idea, glass bricks, and the demands from the, how do you call it in English? That is a good-looking monument, are very high, and only Winnie Maas was allowed to build this in glass, and this should remain in bricks. But Winnie Maas is good, he can talk very convincingly. He said, can we not let the glass slowly be transformed into real bricks? Yeah? And they said, oh yes, that can be possible, halfway through. And then he said, no, I want a little bit more, and we have one here, and then slowly it will start. And he got his way. The client showed this design to a few of the big fashion companies, and he said, how much rent do you want to pay per year? For a period of 3 years. And Chanel made a beautiful offer, and then he said to us, go and build it. I said, I need a lot of money to do the test. No problem, you go and test it. Till he saw the amount which I needed, and he said, oh, can it be a little less? And then he said something very unwise. He said, if you only concentrate to the glass bricks and leave the rest of the glass structure, the glass window frames, and the glass itself, and the glass doors, leave that to me. I find a contractor who can do it for me. I said, okay, we put it on paper, unfortunately, very unfortunately. And we started building. First was finding somebody who could produce these bricks, make those bricks. And we needed about 7,000. They finally found people from Italy who could make it. We have a lot of glass industry in Italy, due to the heritage of Venice, which is a beautiful glass industry in the Middle Ages. And here they produced the glass in the little molds you see over there, where they were brick. And it's very complicated to make glass bricks. Here you see, as I explain it, how I explain it to the students. You take the glass out of the very hot furnace over here, put it in a mold. It cools down very quickly, to about 800 degrees in 60 seconds. Then it has to cool down very slowly, very equally, till it reaches about 20 degrees after 3 days. This costs a lot of money. We calculated that a brick costs about 50 euro. So if you need 7,000, that's a lot of money. But the client was very enthusiastic. And, okay, we're going to make it. And he made a good deal with the Italians, as we Dutch can do. So we had to start. Here at a big hole to be filled in with glass bricks. We built a complete closed area around it, which always must be around 20 degrees with a humidity of about that. And the client says, no problem, we have to pay it. Of course, we did a lot of tests in the laboratory in Delft, how strong it is. Because we could only paste the glue here, and we selected, after a lot of tests, we selected the glue, the same glue the dentist used to glue your fillings in your teeth. So there's no problem with humidity or whatever things. And we tested the strength, and we got good results, and we go for it. We also made these special parts. We made some calculations, and I have to find out. We came after that one layer of 20 centimeters of glass was not enough. It deformed too much, the tensions were too much. And then the municipality of Amsterdam people came and say, if this will be a monument, can you guarantee that over 500 years the glue will still work? Yeah. You can't, of course. So we must think of something else. Then we say glass weighs a lot of weight, has a lot of weight. So if you put them on top of each other, it starts building up. So I only must make a support at the top, almost at the top. And now we come to this point. We had the floor behind it. This was about 9 meters with the floor. We had to make a support here. So the bending moments wouldn't be too big. So the pressure from the weight of the glass was enough to keep the wind forces from making tensile forces in it, to keep the stability. We made a lot of proposals, but I have no more time for that. But this is the one who won. It's the Gothic proposal with the carrying walls behind. And they are really built. And this allows us to say to the municipality, if the glue doesn't work anymore, it will remain in place. And luckily, they believed us. Here you see them under construction. Here you see the result. People who pass by, there were even accidents of people who pass by on their bike. We ride a lot of bike in the Netherlands, and bumped against the car. And that, people always wanted to touch, is it real glass? Then there were cracks in the glass of the window frames. And the client was, whoa, what's happening? It was in a national newspaper. And it was, oh, and they called us over and said, oh, well, you made a mistake and it cracked and cracked. But it was not the crack in the glass bricks, but in the glass frames of the windows. So we escaped, and luckily we had mentioned it in a letter. So the client was very, whoa, and then he said, is it bad that there are cracks? No, structurally it's not bad. Oh, we leave it like that. Few images. And here are a few images. And now it's another company who pays more rent even than Chanel. That was it. Okay, thank you.
So you said glass is water.
Yeah.
And you also said don't work in construction.
If you want to have good brains and sleep at night well. Yeah.
Okay. Your biggest nightmare as an engineer?
Biggest nightmare? To have a client who has a
same.
lot of ambition, but has not the budget for it. And who don't want to pay for research. Yeah? I always say to clients, it can be built, but it costs you like this. Like I said to the very rich man who owned those companies, the crystal houses, I said, it costs you a lot of money. He didn't care because he had made another calculation. This will be my rent, this will be my building cost. And he said to me in a weak moment, in 5 years I've earned back the investment. Think of that.
And it was the most expensive facade I ever knew about. I remember that situation.
Yeah.
Okay, thank you. We are super good on time. We're kind of 10 minutes late in total, which is, I think, absolutely awesome. Evan de Brinke, the facade and glass person at ABT, and I asked him also for mistakes, but he's also going to show mistakes which are slightly bigger. And
you will see cracked glass.
We will see cracked glass. Well, I leave it like this. Off you go.
Thank you. Thank you for being here. We work on cutting-edge projects. I have a history together with Rob, and he showed some very nice projects. And to me, working on cutting-edge projects is like walking on the cliff of possibilities. And sometimes I make one step too far, and then I fall. But in the end, I will crawl back. Literally, it's like living on the edge. Maybe that sounds a bit like rock and roll. It is, because sometimes I have the same number of sleepless nights when I'm working on those projects. And the devil is always in the detail. I'm together here with Gert-Jan. Afterwards, we'd like to catch up with you and talk about projects. And before I go to 3 mistakes, I will first introduce ABT a little and talk about the Dutch law, which is very interesting to show. We are based in 3 countries, Netherlands, Belgium, and in Germany. And what is interesting, we are part of a bigger picture, which is a holding, Oosterhof. And what is very interesting is that we have an innovation center. Usually we innovate during lunch or in the weekends. We say, no, innovation is important. We have we see it as a project. You start an innovation and you end it, and you get a budget. That's how we see innovation. And this is how ABT is organized. We have everything except architecture and construction. And we have, of course, the specialism which we all know, structural engineering, facade engineering, and the rest of it. We do not have business units. The projects are the business units. You have a project, and those by the engineers you need. And that's how we can give you integrated consultancy. Rob already showed you, we did the structural engineering and the facade engineering for this project in Antwerp. Also for the structural engineering for this theater in Spain, in Amsterdam. And what we always try to do is to have a long-term relationship with architects. This is Kaan. We made this courthouse in Amsterdam, but we're also working with them for this terminal for the Schiphol airport. Rob was telling about MVRDV. We did one of their first projects in Hanover, and lately we also finished the Boijmans depot in Rotterdam. OMA, of course, important with the water in the facades. And well, if I describe myself, I would say I'm a structural engineer with an integrated mindset and a passion for glass. I work at ABT, I innovate at Quake, I give lectures at the University of Darmstadt and Delft, and I'm also co-writing the Dutch glass standards. One of my first projects that I got from Robert back in the days was making this nice swimming pool in Marbella. Of course, I worked on the Crystal Houses project, very nice things, and I also made the big Ferris wheel in Dubai, where we have double curved glass, 5 by 10 meters, and a Rolls-Royce Phantom can drive in. This is another project in Eindhoven, glass boxes. I will tell more about that later on. And we made this hybrid glass stair, which is ultra thin. The architect asked us, can you make a stair which is very thin? And I would like to see no bolts at all. So what we did is that we made the balustrades as loading bearing beams, and the concrete stair is hanging from the glass. And you see no bolts at all. Well, we also work with artists like German Ermich. This is the Instagram pavilion in Cannes. Also a restaurant in Zurich. And this is Sabine Marcelis, where we made some very nice objects for a light exhibition in Saudi Arabia. Okay, this is what we do for a living. Now about something, the Dutch rule of law. If I compare it to the more, let's say, Anglican system, I think that's how it works in Germany, is that you have a lot of lawyers. When something breaks, the client will ask his lawyer to call the contractor and the architect, and their lawyers will call you, and in the end you need a lot of, I think, lawyers. And to me, it's a more black and white system. One's to blame and the other one has to pay. The Dutch system is a little bit different. It's about reasonableness and fairness. So, when there's something wrong, we go to sit together at the table, put it on the table and say, okay, what happened? Who's to blame? And if we agree who's to blame, then we'll go to our insurance and then we repair it. Position 3, if we do not agree, okay, then we go to a lawyer. So it's well, a bit more gray, 50 shades of gray, you see them here at the backing. Okay. My first lesson, sometimes you need a change of mindset, and I needed that for this project, which is in Eindhoven, a glass box. The architect, which is Union Studio, would like to have this box of 5 by 7 meters. And I think everybody knows in this room that you cannot get one panel of glass which is 5 meters wide. So we had to redesign it, and we helped him. And we thought maybe it looked like the envelope, how envelope of structure works, the envelopes like this. And we thought of maybe splice laminate things so we can make a flat panel. But that didn't work out. So in the end, we made more like a shell structure. You can see it, there are some sections here. So it's a more 3D, because then I have this well-known property of glass. It's very good under compression. like a shell, it's in compression, and bending is not the best idea. So we had this shell, and it should be fully transparent, so no steel is allowed here. So we engineered it, and so we thought of, let's glue all the joints here. Let's glue them. It's very easy, and then they were done, aren't we? The difference between short-term strength of glue and long-term is a factor 10. So it decreases a lot in time. So we calculated a lot. We did, and we tried to avoid peak stresses. So we did nonlinear analysis. We tried to have bilinear material properties, and even cut out the corners with glue and hope that it distributed better. It didn't work out. We had 20 types of glue, and we even had beta versions of a producer, which we knew best, and after 3 days we had creep. So, back to the beginning, I was at a point where I was at this cliff of properties where I failed. But I crawled back. And I thought, well, let's go back to this well-known property of glass, which is compression. So I had the idea, why not make little notches? Where little notches, and then I have a mechanical connection. So that was the big idea. So we make a little notch here. I was afraid that the architect didn't like this thing, but he said, oh, I've never seen it before. That's why I like it. So I made this notch here. And you must imagine that there's something about 400 kilograms standing on it. So it's 2 times 10 millimeter glass, so use your fingers, and somebody of 400 kilograms will stand on your fingers. That's what we're doing here, cutting edge. So we put that in a finite element method, and we also had this difference in tolerance, so we always modeled that in our calculations, and in the end we had to install it. And designing it is something different than installing it. It was mentioned before today. They made this nice wooden scaffolding, and you can see how big it is. You can see the person here. It's 5 by 7 meters, and they had these temporary fixings here to keep everything together. And here you can see how it's tied up. So here you can see the notch again, and you see this how it's tied again. And then we glued it, and it was finished. And here you can see that it's fully glazed. So the cantilever is this top panel, and you can see all the notches here, and that way I have a mechanical connection. Sometimes you fall off your cliff, but you come up with an innovation, and it's very nice indeed so far. I will not go there. The municipality was afraid that something could happen to these glass boxes. So no, nothing will happen. I mean, who can throw a stone? I mean, it's almost at 70 meters. And then, of course, we got Corona. What happened is, of course, that there were riots, and we had this picture from Eindhoven. Luckily, nothing happened here, and also at the Crystal Houses during the riots, there were containers placed there. So there's always a solution, let's say. And for solutions, there's one key to success, and that is collaborate. Maybe we are the engineers, but you need designers, someone who build, and of course, like a university of Darmstadt or Delft, please test things. Okay, so the lessons I learned is, well, maintain ambition. So it's the easy way. If you fail, okay, well, let's change the ambitions. No, keep track, and despite setbacks. And persist in finding another way. I mean, there are other ways, and talk to people who have other ideas. Don't do it yourself. And, well, sometimes you have to rethink engineering. Lesson 2. Sometimes circumstances change. And what I mean by that is this, it happened as this project. This is the forum in Groningen, where we did the structural engineering, geotechnical engineering, and the facade engineering. It was a very nice project where we had a flush detailing of the stone and the glass are in one plane, and this is how this shape was designed by the architect. It has been cut off, And this whole atrium was punched through horizontally, like that. Easy design to say, okay. But then you have to make it. It was punched from this rectangular block. So all the windows are parallelograms. You can see it on the top, on the left. Each window is different. And that's the easy part, because sometimes there's also a fold in it. So that's what we had to solve in this project. Well, we survived. But then there's another thing in the Netherlands, and I think it's in the news, not in the Netherlands, but in Turkey. We have gas fields. Just like in Russia, in the Netherlands we have gas fields. And one problem is it causes earthquakes. Also in the Netherlands. And what's different in the Netherlands is that this, it starts at 3 kilometers depth instead of, well, let's say in Turkey or in Italy at 30 kilometers. What they have in common is that the peak ground acceleration, so how fast will the ground move, is the same, is 0.24 g. It's the red zone here. So it's almost the same as in Italy or in Turkey. That's what the Dutch government thought then. Now it's 2.5 times less, but back then we thought that would be the idea. So what do you do when the circumstances change? And what if the contractor is already with the structural works at first floor? We had to redesign everything. Of course, big interest, big contractors, sometimes you have a little argue, but we thought, okay, we have to work together to get things done, because we didn't know anything about earthquake engineering. Also the contractor didn't. So we worked together, and we did a risk analysis, high-risk building elements, and we looked at it. What will be the forces during an earthquake? So is the wind load governing, or the earthquake load? And that's what you see here. On the left one, you see how the concept was of in the contract. We had approximately, let's say, 20 mils of detailing, and what we did during earthquake, we need a bigger spring. We needed more deformation. Also, what you saw in the Doha project in Saudi Arabia. So here you see some details, and what we improved, we came from 20 to 30 mils in earthquake zone. We could say, generically, we changed everything, but we also kept in mind some facades are tilted forward and some are backward. So this is better because the self-weight is against all those earthquake forces. So we had to find a solution for everything that is leaning forward. And this was if you look at the original detail, this wasn't sufficient anymore. We had this faceted glass here at the top, and you can imagine that it's okay for wind load, but if it's also an earthquake, then that's not sufficient anymore. So that's why we had these little hands for the facades which were tilting forward and not leaning backward. Where they're leaning backward, the self-weight was enough to keep it in place. And it's a pretty nice project, I think. So if circumstances change, you always have to question yourself and challenge yourself. Why do I need something extra? Do I need it extra? And believe in your knowledge and know where it ends. In this project, we didn't know anything about earthquakes. So we asked a company from New Zealand to help us out. So try to know where your knowledge ends. And of course, work from coarse to fine. I could place hands at every facade, but then it would be very ugly. So work from coarse to fine. Last lesson. It's the play. When you have a failure, I see it always like a play, a play of interests. And I use this project, which is a castle, which has a glass bridge, but it's about the glass winter garden. It's made of fully glass, and here you can see how it's well situated in this landscape. And well, what I would like to challenge is this quote, and it says, "The lie that suits its best is what we call the truth." It's a nice fully glazed structure where we have steel inserts, which are the only steel parts in the whole project. Of course, hey, we know how to glue a corner. We made a little setback here so it could rest on the glass. Of course, you have some elements which can be glued together. Nice ideas, and here you can see how we detailed this fully glass thing. What happened in 2015 during construction? One of the 4 beams broke in the middle zone, and it was 24 degrees outside. It was already the roof was already there, so it was kind of hot on top of it. And oh, ta-da! Here we see the butterfly, and most people who know damage of glass, we say it's nickel sulfide inclusion. Well, here you can see the organogram. It's very simple. We have a client, we have a contractor, we have a subcontractor for the glass, and well, I was there. Well, we sat around the table, we looked at it and said, okay, it's the middle pane, it's about here, it's a butterfly. Well, conclusion should be nickel sulfide inclusion. We agreed. Fortunately, there was already a spare beam. It was a little bit more curved, it was a centimeter longer, but it was still there. It was during construction time, so replace it, done. After completion, 1 year further, exactly same temperature, the same beam broke again. Not in the middle, but at the support. I could make a picture, because I was here's a balustrade. I could make a picture like now this, and no, it looked like that, and to me it was a butterfly. Well, but it was during the holidays, and I extended the organogram with the glass supplier, and the glass supplier called his friend who worked at the notified body. What happens is, you know how notified bodies work. If they get information, they should write it down. They cannot ignore it. So the glass supplier, he made a site visit. He took his friend, because they're friends. He took his friend and he showed him, do not look at the beam. Do you see the facade? It's tilting like this. And you see that detail there? I mean, it's like that. So, well, the notified body had to write everything down. So in the end, they came with a list what could be possible causes of everything, and nickel sulfide, oh, that's very questionable. Well, but have you seen the other things which are happening there? So, well, I was on holiday, so I thought I couldn't not be in attack mode, but more in a defense mode. And how can I set up my defense? Well, about overload, about impact, about, well, maybe other inclusions, I don't know. Then we had the method of forensic engineering, which is very, very helpful. You do some analysis, field survey, you look at causes, and then you validate the most likely cause. So a structure, okay, can it maybe be hinged, or does the roof buckle, something like that, structural engineering, or a field survey about geometry and tolerances and production, and well, here you can see the total list, and it's half of the list which could happen. And from there, and then it gets interesting, how about possible cause? And I have to verify and falsify them. That's a funny thing. Because of overload, the verification is, yes, we only did a simple 2D calculation, so yeah, that can be everything. So, but we also could falsify it because the fracture was in a neutral line, and we also made a 3D analysis afterwards, and we had the upper limit and lower limit of all the tolerance, and well, it's still okay. The most interesting thing is the material. How could it be that it breaks? The verification is it was a high temperature, it is a random position, and the glass was made from the same batch. Falsified, there was this test certificate from China. Why could it be nickel sulfide inclusion then? So we ended up with 2 main conclusions, and well, we went to the client again and we discussed it with him. So there might be 2 solutions. And on that day, we also made a site visit. And I had a ladder, so I didn't have to make my picture like that again. And I made more pictures, and then, ta-da, finally, There it is. My nickel sulfide inclusion. So after 2 months of forensic engineering, I was right. So what I learned, damage is a lesson, is just a play of interest. Nothing more, nothing less. And employees at notified bodies are humans too. I could make the same of architects, of myself, of engineers. People have opinions. They're not always unbiased. And forensic engineering is a very helpful, unbiased tool. So, to end this session, I think even if we are talked about today about damage control or designing innovation, it are creative processes. And, well, sometimes, well, some unprecedented turns, setbacks can unbalance you. But if you can overcome that, you feel unbeatable. And you have to turn a setback into an opportunity. So be critical and optimistic and use everything you can. Thanks.
Unbeatable.
Yes.
What was it? Know your end of the knowledge.
Yes.
When do you get sleepless nights?
When I do not have the solution yet.
For mistakes or for new designs?
Both. Both. I mean, I'm always trying to improve myself, the better me, and that's
The better me.
Yeah, finding that out, and that's sometimes.
Rob, do you have sleepless nights? Sometimes. It's an interesting thing. These are, they say, the structural engineers. They actually have this responsibility for life, and that's a different story than us facade guys who are just making things watertight. I think that's actually quite a fair comment to see. So when you design this kind of things and you're reaching to this edges, that's quite a point. We are super good on time. This audience didn't ask any question at all. I'm very open if you have a certain question to one of these speakers. They all sit there.
I think Isabel had a question.
If not, I close. Thank you.
Okay.
It's going to take me 45 seconds to wrap it up. The usual thing. Glass breaks. That's what we learned. Glass is black. And you're supposed to use as much as possible. Monitoring is a must. I absolutely copy this. Complexity, adaptivity, and design a role model is something. Maybe alternative materials. That was a comment from Holger. Rob thinks glass is water, has sometimes sleepless nights, and is worried about clients with too high ambitions. I actually copy that one a lot. And from the last one, from Erwin, we had feel unbeatable but know your limits. Thank you. This was about mistakes. So I heard a lot of bitching of architects, dear friends. I'm an architect. A lot of bitching of construction sites, but also learned that we have to go there and make sure that things are really installed. Interesting-wise, Christian, no bitching about system suppliers. I'm not sure if this is correct in an environment of system suppliers. So that's something which is really to be addressed. We learned a lot about communication. We learned a lot about technology, and we also saw these professionals standing up and trying to solve their problems. Thanks to the speakers, really. Thank you for coming and taking this challenge. Thanks for the technical team for taking care, and thanks, Christian, for inviting us, paying the bill, and paying the hotel. Thank you. And over it is.
Discover Next, the studio for facades and design. Next is the platform for innovation in the field of building envelopes, for inspiration, information, and communication. Initiated by Vicona, with leading industry experts as Next partners. Next is a unique concept which is constantly evolving and bringing the future of cities to life.